All right, now that we've taken a look at determining a rate law and determining the exponents and k and determining that rate law experimentally, now let's take a look at developing our second method to develop the rate law and get that information. So in order to develop this thought, we gotta borrow some ideas from calculus. All right, so what I'm going to do is go step by step. I might be going a little bit slower if you've had some calculus, so just bear with me. All right, if you haven't had calculus, not a problem. We're going to keep things as simple as possible. So in order to understand this without calculus, I'm actually going to go back to an idea that we started about in the first kinetics video when we were talking about the student concentration, how measuring students leaving the room. Okay, so to keep things simple, let's say we start with 100 students this time. We know that it's exact. We can count that there are exactly 100 students. Okay, so it's 100 with a decimal point. We know that's an exact number. So what is that initial concentration? Well, that one's pretty easy. It would be 100 students in the room. Okay. All right. Now, the rate of departure may or may not be a function of concentration. So that is, do students leave the room at a constant rate until it's empty, like 10 students a minute? Or do they leave, or does the rate decrease as the room empties, like 10% a minute? So that's a good question. So we got to figure this out. So what would it look like if we wanted to measure that? What would that expression look like? So basically, we could write a rate law for that. And the expression would look like something like this. The rate of students leaving the room would be equal to a rate constant k times the concentration of students in the room, students leaving the room, okay, and then raised to the power of m. All right. Now, we talked in the last two videos ago, we talked about what the exponents mean. If the concentration's doubled, then the rate doubles. That's if m equals 1. So it's a first order. If it's second order, you double the concentration, the rate quadruples. That's second order. Now, here we talked about one type of reaction where, let's say, the rate of departure is not a function of concentration. So you double the concentration and it does nothing. It doesn't do what you expect it to do. In that case, we say that the exponent has to be 0. Okay. Now, alternatively, the rate of departure might be 10% of the room per minute. Okay, so what I'm going to do is let's say we've got two different plots. What if we have 100 students leaving the room, and what we're going to look at is, let's say we keep the rate constant, so it's constantly 10 people leaving the room. Second column over here, we're looking at 10% of the students leave the room. Okay, so at time t equals 0, at the initial time, you still have 100 students in both situations. In 1 minute, for the straight 10 people, you're down 10 people. Okay. For 1 minute after, same thing. 10% of the students leave. So that means you're down to 9. You're down to 90. Okay, so we're doing okay. Second minute in. If you go with a straight 10 people, you're down to 80 for the first case. Now this time, if for the second case where it's a 10%, 10% of 90 is 9 students. So in this case, that's how we get to 81. So you still have 81 students in the room. Now, if I go another minute, if we go the constant 10 students a minute, we're down to 70. Okay, so we're down 30 students in this situation. Now, if I take 10% of the students in the second column, that would be 8.1 students. Okay, so now that gives us 72.9 students left. So we've actually divided someone in that, and we have 9/10 of that person. The other 10th is out in the hallway. If we go another minute, if we go with a straight 10 students a minute, we're down to 60 in the first case. For the second case now, we're down to 7 About 7.3. 7.29, let's round it up to 7.3 students. So now we're down to 65.6 students. All right, so, okay, we can keep going for every 10 minutes, so until the first case gets down to 0. But what happens with the other case? Even though it's starting to approach 0, I mean, even though it's going down, it was going down pretty nicely. It seems like this number is starting to slow down. I mean, we get down to 65, 90, 59, 53, 47, 43, 38, 34. And with a minute, if we went to 11 minutes, we'd be at 31. So if we were to graph these two, these two plots and put them together, the blue plot, that's the constant 10 students leaving a minute. Okay, so eventually we get there. We get down to 0. But if we look at this orange plot where we've got the 10%, it starts to approach 0. But it's going to take an awful long time to get there. Okay, it's going to take an awful long time, and you may never touch 0. You're always going to have like, a number that's going to be like 10 to the minus 12th or whatever. So which of the two plots take longer for the room to empty? It's the 10% one, because this plot does not reach 0. It approaches 0, but that never ever gets to 0. Okay? So for the 10% case, what is M? Well, in this case, M would be 1. So it would be a first order reaction. Okay? Now, in that sense, what would K be? K would be 0.1. Okay. Now, what is this second case called? This is actually called exponential decay. All right. So what we've just done graphically and talking our way through this is a result of a calculus analysis. So we're actually doing calculus even though we haven't done a derivative or an integration. So how about that? So this method that we're using in order to help us figure out the rate law and the exponent, we call this the integrated rate law. The integrated rate law method. Okay. And so in order for us to come up with an equation, and that's essentially what we're trying to do. We're trying to come up with an equation that mimics the rate law. So if we have a generic equation for a rate law with a single reactant, the rate would be equal to the rate constant K times the concentration of A raised to the power of M. Okay, and this would be equal to the negative change in the concentration of A divided by the change in time. Now, what I'm going to do, though, to make things a little bit easier this time around, is I'm going to assume that M is 1. Okay? So we're going to make an assumption that M is 1, that this is first order. If that's the case, then the integrated rate law would look something like this. You would have the natural log of the concentration of A at a certain point in time, t, divided by the concentration of A initially, so I'm going to put A naught. This is equal to negative KT. T is the time. K is your rate constant. Concentration of A is at a certain point in time, and then this last one is the concentration of A initially. If you have 3 of those pieces of information, you can solve for the 4th. Now, what's really cool is that you can take this equation, and by the way, this is a really, really important equation. It's so important, I'm going to highlight this, and I haven't yet done that in this course, so you can tell that this is a really important equation. If I was to rearrange this equation and get into a straight line form, like y equals mx plus b, the equation would look something like that, like this. The natural log of A, of the concentration of A at a certain point in time t, is going to be equal to negative kt plus the natural log of the initial concentration of A, where y is going to be the natural log of a concentration of A at a certain point in time t. M would be negative k. X would be your t. And then B, your y-intercept, that would be the natural log of the initial A, initial concentration of A. And so if we were to, and so that's kind of what we did. We took a curve, we took an exponential decay curve, and what we did was take that and put it in a straight line. As long as we graph the natural log of the concentration of A over time, we get a straight line. So that's pretty cool. Now, why is the second plot, getting the straight line, why is that useful? And the reason why we'd want to look at the second line, to get that straight line, we want to check the quality of the data. So why do we care about that? Well, if we have outliers, we want to make sure that this line is going to be the line of best fit as well. So we want to make sure if there's outliers that we can point those out in the graph, in the curve. All right. So this brings me to a really, really important point. The straight line in this second example that I'm circling, the straight line, example B, will be straight if and only if, and I'm going to underline that, if and only if the reaction is first order in A. That's it. So that means that the reaction has to be the exponent has to be m equals 1. So this is a really important point. The straight line will be straight if and only if this is a first order reaction. All right, so now we got to explain what that means. What does that statement mean? This is an extremely important statement, so let's explain this. So what I'm saying is this. If the graph of the natural log of the concentration of A versus time is a straight line, then the reaction rate would be this. The rate would be equal to the rate constant K times the concentration of A raised to the first power. Okay. Now, if M is equal to 2, 0, or 2, or 3, or continue on, we would not have a straight line. And so that's it. As long as you have a first order reaction, this equation will work. This highlighted equation is going to give you a straight line. That's only if you have a first order reaction. If you've got a second order, you got a third order, or you got a 0th order reaction, you will not get a straight line. And so that's that second curve, or that second line. Seeing that straight line tells us that we've got, this is confirming that it's a first order reaction. Okay. So that gives us time. Now it's time to see how this all plays out in a problem. Okay, so let's try a problem out. Here's our problem. The compound aziomethane decomposes in a first order process in this method. And I have the equation here. Okay. The rate constant for this reaction is 2.55 times 10 to the minus third seconds to the minus first power. Okay, so wow, we're given a rate constant already. That's half our battle from the last problem. All right, part A, write the expression for the decomposition rate. Use AZ as shorthand for the compound aziomethane. Okay. B, write the rate law. C, write the integrated form of the rate law. D, if the initial concentration of aziomethane is 1 molar, how long does it take for this to reach 0.5 molar? Part E, how much longer for the concentration to reach 0.25 molar? Part F, for the same initial concentration, what would be the concentration after 300 seconds? All right, so we've got a lot of stuff to take a look at. We got some stuff to figure out. All right. So the first one, write the expression for the decomposition rate. So what that would look like for part A, the decomposition rate would be this. The rate would be equal to the negative delta change, negative change in the concentration of aziomethane divided by the change in time. So that's how part A is asking for. Write the expression for the decomposition rate. There it is. Now part B says this. Write the rate law. Well, knowing what we know, since aziomethane is the only reactant, the rate would be equal to K, the rate constant, which we actually know, times the concentration of aziomethane. Now, we're going to assume, however, well, we don't have to assume because we're actually told it's a first order process, so that means this is going to be raised to the first power. So we know that the exponent is 1. Nice. All right. So that's part B. Part C. Write the integrated form of the rate law. So here's what we're going to do. We're going to take that equation that we actually got in the last part, the one that we highlighted. We're going to take this equation and adapt it for this problem. So here's what we got. For part C, we're going to take the natural log divided of the concentration of aziomethane at a certain point in time, T, divided by the initial concentration of aziomethane. That's going to be equal to negative KT. There it is. That is the integrated rate law. All right, so part D. If the initial concentration of aziomethane is 1 molar, how long does it take for this to reach 0.5 molar? So all we're going to do is take for part D is to use the equation that we have in part C, except we're going to solve for T. All right, so we're going to use that equation. So the initial concentration is going to be 1 molar. Okay. Divided, that's going to be underneath. The concentration we're going for is 0.5 molar. And that's equal to negative K. In this case, we're told that K is going to be 2.55 times 10 to the minus third seconds to the minus first power times T. So we're going to solve for T. Okay. So the right-hand side comes out to be nice, but if I take 0.5 divided by 1, that still gives me 0.5. If I take the natural log of 0.5, that will give me negative 0.693, 314. And that's equal to negative 2.55 times 10 to the minus third times T. Now I need to divide both sides by K, so that way T gets by itself. So T would be equal to negative 0.69314 divided by negative 2.55 times 10 to the minus third. And that value would be 272 seconds. So there's your answer for part D. That's how long it would take for the concentration to be half of its initial strength. Now for part E, how much longer will it take for that concentration to reach 0.25? All right, so I want to know how much longer is it going to take for this reaction to go to 0.25. Same equation again. So we're going to start with the equation from point C, except we're gonna pop in our values. So the concentration of aziomethane at a certain point in time T is going to be 0.25. The initial concentration is 1. And then this is going to be equal to negative KT. So we're solving for T still. So it's going to be negative 2.55 times 10 to the minus third T. Okay. So in this case, So in this case, if we take 0.25 divided by 1, that should give us 0.25 divided by 1 is going to be 0.25. If we take the natural log of that, that would give us, on the left-hand side, that should be negative 1.386 is equal to negative 2.55 times 10 to the minus third T. All right, so if I divide both sides by negative 2.55 times 10 to the minus third, I get negative 1.386 divided by negative 2.55 times 10 to the minus third, and that should give us about 543 seconds, about 544. It comes out 543.644. So let's call it 544. Okay, so how much longer is it going to take to answer part E? Well, if we take that time that we just calculated, 544, and we subtract the time that it took to get to half the strength, so 272 seconds, the additional time should be 272 seconds. So it's actually double. How about that? All right. Now, so that was part E. Part F says this. For the same initial concentration, what would be the concentration after 300 seconds? All right. So what we want to do is take our equation. We're going to solve for the concentration of aziomethane at a certain point in time t. Okay. So we got the natural log of the concentration of aziomethane at a certain point in time, T, divided by the initial concentration, which is 1. This is equal to negative K, which we know, times the T, and the T is 300. 300 seconds. Now, what's nice is we know that for 300 seconds, it's going to be between 544. The concentration should be somewhere between 0.5 and 0.25. So already we have a pretty good indication of where this number should lie. All right. So what we need to do, let's get the negative KT part. Let's get the right-hand side figured out. So 300 times K, which is 2.55 times 10 to the minus third, that should give us negative 0.765 on the right-hand side. And so it's going to be the natural log of the concentration of A divided by 1 molar. All right. So since it's A over 1, anything divided by 1 is going to be that number. So we can actually simplify this a little bit more and say that the concentration of aziomethane is going to be equal, the negative log of the concentration should be negative 0.765. All right, so now we got to undo that number. We got to undo the natural log. So we're going to raise, so that's going to be our exponent for E. So E raised to the negative natural log, E raised to the natural log of concentration of aziomethane is going to be equal to E raised to negative 0.765. So that way the concentration of aziomethane is going to be equal to E raised to negative 0.765. And that number should be, if we take E raised to the negative 0.765, that concentration should be 0.465 molar. So there it is. That's our concentration. So that's a pretty cool problem. All right, now one more thing I want to talk about before we leave this away, because we kind of stumbled on something. We figured out what when the concentration is halved, we saw that, and then we went to the concentration where it was quartered, and we saw that it was double the time. So there's got to be a pattern here. So here's what it's saying: derive the general expression for the time it takes in a first order reaction for the concentration of reactant to reach half of its initial value. Okay, so let's try this. So here's the equation as is. Natural log of concentration of A at a certain point in time, T divided by the initial concentration, okay, is equal to negative KT. So what I'm saying is that for a certain point in time, we want that to be the initial concentration, okay, divided by 2. We want half of the initial concentration. And so that's what we're going to do. So if I was to replace A sub t with that expression, we'd have this natural log of the concentration of A, the initial concentration of A divided by 2 over the initial concentration of A. And this is going to be equal to K, negative K times T. But for the T, what I'm going to do, since this is going to be the amount of time it's going to take to get half the concentration, I'm going to write T1/2. So that's pretty cool. Now, if we solve for T, we got to figure out what's going on. So on the left-hand side, where you have A, the initial concentration of A divided by 2, divided by the initial concentration of A. Well, let's assume that the initial concentration of A was 1 molar. So if it's 1 divided by 2 divided by 1, it's still going to be 1/2. So it's going to be whatever's on the top. So in that sense, you're going to still have the negative. You're going to still have if we rewrite this, you're going to have the natural log of 1/2 is equal to negative K T1/2. Now, if we solve for T for the time, if we solve for that time, we have to divide both sides by negative K. So we would have natural log of 1/2 divided by negative K. Or we could rewrite this as negative natural log 1/2 over K. Now, if we evaluate the negative 1/2, if we evaluate the natural log, that's going to come out to be a negative 0.69 times the negative sign. That's actually going to give us a positive. So then we would get this, that the time to get to half the concentration would be equal to 0.69 divided by K. And so this is actually a really important equation. So this is actually something called the half-life. This is the amount of time it's going to take for the concentration to be cut in half. So what is very interesting about the relationship between the half-life for a first-order reaction and the initial concentration? Nothing. There's nothing really exciting here. This only works, however, if you're working with a first-order reaction. Okay, so we have this image. Now, so this is definitely an exponential decay curve like we saw previously. And over here at the top, this is our initial concentration of our substrate. Okay, and so with the time it takes for the substrate, the initial substrate, to get to half of its original concentration, that's what we're defining as a half-life. Okay, now at that point where we're at the half of the original concentration, if we have that again, notice that it's going to take the same amount of time to go to, to have that concentration. So that we say that that's another half-life. So what's really interesting about this curve as we go from one concentration to the next level, it's that the half-lives never change. It never changes. Okay, so this is actually, we actually kind of just stumbled upon the third method of determining rate change. So the first method was the method of initial rates. Second was the integrated rate law, and we're still not quite done with that one. But the third one is to use the half-life of the reaction, because different orders have different life forms. So this is actually a pretty cool tool to use. So as long as a reaction follows the form of a first-order half-life, the reaction is going to be first order. Now, if it doesn't, that means we gotta check out the other orders, and we'll talk about those as we go. All right, so just to review, what are the three ways that we can determine the rate law of a reaction? Well, I just said this, but let's write it down anyhow. The first one was the method of initial rates. That's where we take the experimental data and we try to figure out the exponents, we figure out K, all that good stuff. Second one was to use the integrated rate law. Okay, and we talked about that for a first order reaction already. And then the third way is that we could use half-lives. Now, before we go on to talk about the second and the zero order reactions, there's one more topic that I want to talk about, especially with first order reactions, and that's actually radioactive decay rates. This is something that we're going to talk about when we get into nuclear chemistry at the end of the course, but it's pretty good to bring up here because actually this is it. This pretty much this is in sync with with what we're talking about here. Okay, so like I said, it's an excellent example of first order kinetics, including exponential decay and constant half-life. So if we were going to give the equation for decay rate, what that would look like is pretty much like the same kind of equation as we've seen previously, that we're going to have the negative change in the concentration, which I'm going to use delta capital N for, divided by the change in time. Okay? And that this has to be equal to K, the rate constant, times the initial concentration. Okay? Now, if we're going to describe this proportionality in words, it would go like this. The rate of decay decreases proportional to the concentration. Okay, now if I take this equation, the expression that we've got, and rewrite this in terms of the integrated rate law, what that would look like is that we have the natural log of the concentration of our nuclear species at a certain point in time t divided by the initial concentration is going to be equal to negative K, the rate constant, times t, the time. And if we were to give you the half-life, now that we know how to do that, the half-life equation, either saving time and not deriving it, half-life would be equal to the natural log of 2, which is going to be something like 0.069 divided by K. Okay, and so this half-life only works if the reaction is first order.